Welcome back. In this video, we're going to be looking at the relationship between light and how it relates to our understanding of electrons. Also, talk about the electromagnetic spectrum briefly and get into some calculations that we will be doing using light. But first, the nature of light. The reason why we're kind of taking a look at this now is that much of our understanding of how electrons behave in atoms comes from studies of how light interacts with them. Probably understand that light is a form of energy. Movement of electrons we know as electricity, which is a form of energy. And how these two things interact can tell us a great deal about either or. And light is kind of unique in the sense it has both properties of particles and waves. And especially this wave portion of it, just like mechanical waves like you'd see on a lake or an ocean or a pond, all waves can be described in these various terms: amplitude, wavelength, frequency, and wave speed. Okay, I know a lot of you are not going to be very familiar with light, so it can be beneficial to you when you're thinking about these terms to think about, something that you're more familiar with, like water waves. First of all, amplitude. It has a symbol of a capital A, and this is just defined as the height of a wave from origin to crest measured in some unit of length. If we're talking about light, we may be looking at these wavelengths are really tiny, so we will probably not be looking almost at millimeters, the smallest metric prefix you're required to know, but we will be looking at things like micrometers or microns, nanometers, and possibly some other very, very small wavelengths, units, and these conversions would be provided to you. Not the millimeters one, but the other one. Now, down here in this picture, we've got some information, right? You notice that the amplitude here is only defined as from the origin to the crest, either from the origin going up or the origin going down, right? It's not the entire height of the wave. That's a big thing that folks can get mixed up with. Next one we'll look at is wavelength, which is given the symbol. It looks like an upside down Y. It is the lowercase Greek lambda. So in the Greek alphabet, it's the lowercase of lambda. And this is defined as the shortest distance between equivalent points on a continuous wave. Right, and this again can be, if we're talking about a mechanical wave, like a water wave, it might, unit of length, probably meters. But if we're talking about a light wave, then it could be millimeters all the way down to nanometers. Again, it's going to be a unit of length. Lastly, frequency is given a symbol. It looks like a V, but it is the lowercase Greek letter nu. And this is just defined as the number of waves that pass a given point per second. And defined as the number of cycles per second. And this is measured in a unit called hertz. You may have heard this term before, probably in the context of maybe a rental car company. I don't know if they're still around. But all hertz is defined as 1 over seconds, or you could also say it's seconds to the minus 1, or you could even get, just say cycles per second. All these three things mean the same thing, which is hertz. Now, our equation for wave speed over here is just equal to the product of the wavelength times the frequency, so nu times lambda. And if you're looking at this equation, if you want to kind of figure out how these two things are related to each other, the wavelength and the frequency, whether they're directly or inversely proportional. This was some vocabulary from Unit 1, directly versus inversely proportional. If you look at this equation over here, this is the equivalent of, in algebra class, you'd see something like x times y equals 1. And what that means is that these two variables, x and y, in this case, wavelength and frequency, are inversely proportional, which means as one goes up, the other one has to go down. All right, so we already talked about how amplitude is defined as this distance, either from the origin to the crest to the bottom or the origin to the top. Wavelength, right, is shown here. It's just the distance between points on consecutive waves. So that could be a wavelength. This distance right here could be a wavelength. This distance from here to here, those are all wavelengths. For electromagnetic waves, when we're talking about light, the wave speed is a constant, and it's given a symbol c. And here is the value of c. This is also listed on your periodic table. On your periodic table, it's listed as 2.998 times 10 to the 8th meters per second. It doesn't matter which one you use. It won't make a difference. And also, since this value is provided to you on your periodic table, how are you going to handle it with singular numbers? Hopefully, you remember that basically anything you get from the periodic table, just treat as a defined constant. Now, right down here is our electromagnetic spectrum. And the way that this is grouped, as you notice down here, it says hertz. And so this is like 10 to the 5th hertz, all the way to 10 to the 19th-ish hertz. So this is just ordered by wavelength, or sorry, not wavelength, frequency. And this right here kind of gives you a rough visual idea of like how the frequency is changing as you go across. And then right here it says that this end represents low frequency, long wavelength, and low quantum energy. So here's right here is also a further reminder of the fact that this is an inverse relationship between wavelength and frequency. Right, as one goes up, the other one has to go down. So over here, low frequency, long or large wavelength. On this end, high frequency, short wavelength. And also, on this side, it's low energy. On this side, it's higher energy. So as you go from this side to this side, it's increasing in energy, increasing in frequency, and the wavelength is getting much, much shorter. And the way that these sections of the spectrum are categorized, you probably have heard of some of these. Obviously, you've heard of the visible light piece. You've heard the term ultraviolet before. You've heard infrared, right? If you remember, the visible portion of the EM spectrum follows what order? For those, the colors of the rainbow, right? Roy, G, Biv. So that's here. And it makes sense. Infra, the prefix infra means below, ultra means above. So on this side, you'd have the red. This side, you'd have more the violet portion of it. And then, of course, you've heard of X-rays. Microwaves, right? This is the frequency range which your microwave at home operates in. And it also is, microwaves and your wireless routers at home typically are occupying the same part of the spectrum. AM radios down here, FM, TVs here, Carmel WHJE, going to be in this area. Microwaves and millimeter waves, right? Millimeter waves, if you are not aware, that's what powers what the machine at the airport uses when you step in and put your arms up above your head so they can scan your body. They're using millimeter waves there. And then X-rays and gamma rays. Oops. So, this is what you need your calculator for. And also need to hopefully know how to put scientific notation into your calculator, because when we're dealing with light, we've got big and small numbers, and that means we're going to have to use scientific notation. So on this first practice problem, if we want to calculate the wavelength of the yellow light emitted by a sodium lamp, and if you're not aware of what a sodium lamp is, these would be, there's used most commonly as streetlights. Not like the red, the stop, go, the red, yellow, green type of thing. But like the lights that are on your street, on the big towers, that go on at night, that have kind of a yellowish hue to them, right? I think there's a drive towards, Carmel's been replacing some, I think, with LEDs or LCDs or whatever, that have a much whiter, brighter light. But these sodium lamps with this yellowish light are very low energy, and they last forever, and they're very efficient. So that's why they're used. But anyway, if we want to calculate the wavelength of the yellow light emitted by these sodium lamps, if the frequency of the radiation is given as 5.09 times 10 to the 14th hertz, the first thing we have to do when we're doing this is remember what symbol is for what, right? Our equation, since we're dealing with light, we C, which is a constant, right? That's the speed of light, is equal to the wavelength times the frequency. So here's our wavelength. Oh, we want to find the wavelength, so we're looking for this. And we have our frequency, which is this 5.09. And C, remember, is the speed of light, which is at 3.00 times 10 to the 8th meters per second, or again, you are free to use the 2.998 times 10 to the 8th. You will get no difference because of how close in value the 3 and the 2.998. Basically, the only difference is this is just written with 3 single figures versus 4. And this we treat as a defined constant, so it doesn't matter. So in our equation here, just have to figure out what we're solving for, which is the wavelength. And I'm always going to rearrange algebraically to get what I want isolated by itself. And to get this by itself, hopefully you understand, you're just going to divide up both sides by the frequency. So you'll end up with this type of relationship. Now we just have to plug in our values. Right? The speed of light is given to us. This is in our problem statement, which is hertz. I would recommend when you're doing this, instead of writing hertz down here, because that can be confusing as you're starting out, right, just put in 1 over seconds for frequency, because it'll make more sense when you're, again, trying to do your unit analysis to figure out what unit you can be left with. Okay? And I'll show you how it goes in the calculator, just to remind you. That's the best. Put it over here. So there is, remember, you do not want to use the times 10 with a caret or not. You want to use the double E key, which is the second function up here, which gives you there. So there's a 3 times 10 to the 8th, and we're going to divide that by the 5.09 times 10 to the 14th. Okay, you notice no times 10, no little caret raised to the 14th or whatever, because this calculator is treating it as this as one number, and everything for the speed light is one number. So you get the answer there, and if you wanted to do scientific notation for you, just move it over, and now we just have to take our significant figures. So how many significant figures should we have? Remember, the speed of light is a defined constant. So hopefully you looked at this, said, oh, there's 3 figures there, so I need to round this to 3. So counting over, there's from here 1, 2, 3. Look back behind it, that's a 3, so I'm just going to truncate it. And I can't forget the exponent. That becomes 5.89 times 10 to the minus 7th meters. Just as a review from the units, I've got meters per second up top. I've got 1 over seconds in the bottom. Right, hopefully that makes sense to you, that this 1 over seconds here cancels out with the 1 over seconds there, leaving just meters. All right, moving on to the second one, was the frequency of the electromagnetic radiation with a wavelength of 5 times 10 to the minus 8th, and in what region of the electromagnetic spectrum is this? So, again, our equation that we'll be using here, looking for frequency, so we're looking for nu, and we're given a wavelength. We always know, if we're talking about light, we always know what the wave speed is because it's that 3 times 10 to the 8th. So in this case, we're looking for frequency. We want to solve for that, and we're just going to rearrange our equation, plug in our values, (5 times 10 to the minus 8 meters). From a units perspective, hopefully you notice that the meters here, it will cancel with the meters down here, but that just doesn't leave you with seconds on top. Right? This cancels out with this, but you still have 1 over seconds remaining on the top. And 1 over seconds, again, is hertz, which is frequency, and you know you've set it up correctly. So let's do the math. 3 times 10 to the 8th divided by 5 times 10 to the negative 8th. Oops, gotta put the negative sign first. And I did something wrong there. 3. No, I'm not multiplying. Alright, calculator says 6 times 10 to the 15th. I just have to keep in mind that there's significant figures involved. So it'd be 6.00 times 10 to the 15th, and you can just leave it as 1 over seconds if you want to. Or you could say seconds minus 1, or you could even say hertz. That unit, those units are all the same. So it's whatever you're comfortable with. I'm going to stop this video here, and I'll see you in the next one.